Well, Halima, where are you? Halima, Jennifer, and Nadia, and Earl for all the hard work getting this put together. And it's great to be here seeing friends and students and some new people. It was a wonderful morning. I'm going to try to do this a little differently, you know. All of you know I'm kind of a different person, and Ted was a different person. So I'm going to try to do this a little differently. My first thought was to do it the way Ted does it, which is to use overheads. Okay. Ted would go to AGU and SEG with about 6 overheads, never more than that, and 1 black pen. And he would do it in real time. He never even wrote them up on the plane or in the hotel room. He would write it in real time. So I started to think about doing that, and I said, you know, it is really a tough task to get this thing, what I want to say, done in that time. Okay. So we brought this here. Earl says he's going to use it also. But I just want to give you a taste and a remembrance, okay, for his way of doing this. Okay.
You're going to have to stand aside from occasionally you can't see.
Yeah, well, I'm only using 2 here. I'm trying to optimize it a little bit.
Are you going to do it in 6 slides?
No. No, maybe 8. But, and the why I'm doing it this way, I say it's Ted's way, but there's another reason, and maybe Halima might know this better as much as all of us. He was a very cheap guy, okay? And I can tell you, he used to have Earl and I going into garbage bins around here in Cambridge, looking for plexiglass, looking for tubes, looking for buckets. And if we pushed him hard, we could go and shop at Sears with about $20. He would not buy a $100 system to make distilled water. We had to go and beg in the base for it. Till people got fed up of us, they would put us out, okay? So he was basically a cheap guy. But one of the things that reflects on me about the cheapness and this slide and this presentation stuff is my first presentation at a scientific meeting was at SEG in New Orleans. And I tried to get Ted to get me 25 or 30 bucks to get some slides made. In those days, you had to make it, and they put this blue background on it, and so. He refused. He said, you have a Nikon camera, make it yourself. I tried, it was terrible. I tried again, it was terrible. And the 3rd time, I picked it up on the way to the airport. I went and I gave the talk, and the slides were terrible. And at the end, the chair was Charlie Swift, who is not with us anymore. And Charlie came to me and said, Dale, this is the most important paper on streaming potentials ever done in geophysics. And you would have won not just the best for this session, but maybe the best for the meeting. But those slides were terrible. And there were just tears in my eyes, you know, about it. Okay? So that's all I'm going to do here. Now I'm going to try to, if I can get this thing off here. I'm going to do about 6 things on the board here. And just say a few words about each one. The first one I want to do is random networks. And mixed-in laws. When you think about this paper, it has some of the best things about TED, and also some of the bad things, which people have mentioned here before. This paper is so difficult to read that very few people have read it, because it represents about 25 years of his work. Then he writes 1 paper, and he doesn't understand why people don't understand it, where he should have written 10. Okay? But, you know, he always felt he should get it to where everything was understood and so forth. But there are some specific things I want to talk about, okay? In random networks and mixing laws, basically what he was doing, you have heard some similar things before, is if you take a rock and there are a lot of resistors around representing the water in each pore, and Ted was trying to find the average conductivity across it. He was trying to find the average permeability across it, and so forth. But there's one thing he came out with after a lot of computer calculations. And he showed that the conductivity was proportional to the geometric mean. And geometric mean is just like a regular mean, but you take the log of all the numbers before. And at the time, I think people didn't think this was a particularly profound thing, okay? But some years after that, when I was a student here, I found in a library, in the best journal in physics, which is Physical Review, that there was a paper written on the geometric mean. So I duly read it, made a copy, came over to Ted. There were 5 authors on the paper. 4 already had Nobel laureates. And it was all about the geometric mean. And what had happened in the interim is that people were seeing that so many things in nature were not distributed in a Gaussian or normal distribution. They were log normal, and in biology and so forth, and it's kind of become today known as the ubiquitous geometric mean, and in dielectric constants and everything. And Ted did this as, it's about a page in the paper, just to give you an idea. That's the kind of power that he had. A lot of physicists were trying to do this at the time. Even over here, IBM had a computational laboratory, a guy called Kirkpatrick, very famous in physics, was trying to solve the same problems. The last thing I would say here is that there is a very famous empirical law in geophysics called Archie's law. And it relates the resistivity of a rock to the resistivity of the pore solution, and roughly speaking is divided by the porosity squared. But it was empirical, and people had tried very hard to prove this. And there were some computer proofs, and people had run it. Yes, it's correct, it's correct, it's correct. But Ted was the first to actually, in an algebraic way, using the word that was put here before this morning, the renormalization group. And when I came here, I had come from quantum physics, quantum solid-state physics, so this was something I knew a lot about. We used to have a lot of fantastic arguments about it. You know, it was never easy going with Ted. It was always a big argument. But he was able to show analytically how to do this and get the exponent and everything and so forth. So that's what I wanted to say about the renormalization group, okay? Okay, let me get to the second one was actually mentioned, I think, I'm going to say maybe by Phil Nelson earlier today. And it's about this thing we call the pseudo section. I wanted to say a few words about it because it has some relationship to things that I do and have done, okay? And the idea is that if we go out to the surface of the Earth, so let's say that's the surface, and we put down 2 electrodes, and we run some current through it, And we measure that at a number of different places. And this continues, so we measure V of I many different places, or delta V of I to be more correct. Okay? We collect this data, we call it dipole. And then you move the current along, and you do the whole thing over, and you keep doing this. Okay? But on a geophysics field trip with the students, which we still run in January here, but this was a summer one, Ted was in Nova Scotia with the students. And they collected data like this, and they didn't really know how to display it. And Ted, as I understand it, just actually sitting down under a tree, said, well, look, I mean, it's pretty obvious what we should do. We should make a 45-degree line there, a 45-degree line there, there. And then here we write down the number for that current and that potential, and so forth. Okay? And so if you keep doing this, at the end, you get something that looks like a triangle, really, is what you get. Okay? And this has become known as the pseudo section, this triangular thing. All right? It's used a lot. It doesn't carry his name, unfortunately. But people started to get a little upset with it for a very simple reason. If the anomaly you're looking at is dead center, it works very well. If it is off center at all, you have terrible offset in accuracy. And that's because these two sides are not imaged. Okay? They're not imaged. Well, interesting story is that I was taking the field trip with students here in the 90s. We were going to the island of Barbados to image caves. And after I talked to even my buddies in the military and so forth, I realized we could not collect data like this and do the imaging of the caves. And at Logan, I came up with a method of improving this, which I passed on to a graduate student agency, and we had it coded. We took the data that way, and down there, using the university's computer, was the first time we got really an accurate measure of a cave. And what I did was to kind of look at this as though it's a flashlight problem. And I said, well, what I really need to do is this portion and this portion, I need to fill this in. Okay? And the way I filled it in was by building an array that goes across the top, but with different lengths of the current dipole. And I call it the left sweep and the right sweep. And if you add to it the pseudo section, if you add these, the accuracy of this thing is just quite unbelievable. Okay? So we've been using it around here hundreds and hundreds of times, and it's funny how it has followed on from a very similar situation with the students on a field trip, and it's a very nice array that we have now. Okay. Brad, how am I doing there for time?
Another 5 minutes or so.
Okay. We'll see how if we get there. All right. Some things have been said about self-potentials. Another area that Ted worked in a lot, and there are a lot of things we could say about that, and lab work that was difficult to do, but we were able to do it eventually. Believe it or not, there was a bubble trapped in the apparatus for 20 years or something like that. It was painstaking. But I just want to make one comment about today what we can do with self-potentials, which really started here. One of the first mistakes is that if we go out to the surface of the Earth And we have some source at depth. And someone said it could be temperature, it could be fluid flow, it could be chemical. You know, most of them are fluid flow today. But there's a big mistake in thinking about this source as a voltage source. You don't want to do that. And in the early days, a lot of mistakes were made in earthquake prediction, etc., because they would take this voltage source and move it to the surface, just like that. Which makes no sense because the earth is conductive. As soon as you put it down there, current flows. So today we know that, and it has really changed the way in which we do SP, is that this source must be a current source. And then as the current flows from that through the conductivity of the earth, we measure the SPs on the surface. So this is how we do the modeling today. This is due largely, and the name was mentioned before by another student who is not here, Bill Sill. Okay. Here in the department, we can do this today in 3 dimensions, and I don't know, we're at least 10 or 20 years ahead of the rest of the world on this. But we can get a full 3D SP inversion. Okay. Well, I should say something about induced polarization, seeing it's what I did my thesis on. When I came in my first meeting with Ted, I told him, look, I'm from the Caribbean. I would like to do a 3D seismic model of a volcano, St. Vincent. And I would like to do at the same time a 3D magnetotelluric of the volcano. And maybe we will be able to do them simultaneously. This was in 1975. And he looked at me and he said, but that's not exciting at all. Now, of course, it still is exciting now. But he said, I forget that at all. Then he looked at me in my eyes and he said, look, I can't teach you any mathematics. I cannot teach you any physics. I cannot teach you electronics. I cannot teach you computing. But you need to learn some chemistry. So you're going to do this subject. And Halima knows I've literally cried holding her hands over the 5 years I took to do it. I didn't want to hear the C word. I didn't want to hear the C word at all. Okay? But I want to tell you one other real kind of important thing that Ted did in this. So somebody already mentioned that with IP, if you have a rock and you have little bits of clay in there or little bits of metallic sulfides, you get this effect called induced polarization. But we can blow that up and just go to a single electrode. And let's say we want to run a current through that electrode. You want to run an eye here. When that current hits this metallic electrode, so it's going to come out as an eye, you get a buildup here of things. They don't, the ions don't go through and into the electrode. You have some energy thermodynamic barriers to pass there. So this has names like overpotential, but it is an impedance increase. So Ted recognized that very early, okay? And he had Angaran, who is here, Africa with us. He had spent his whole thesis showing that in you know, how Ted is again with the equivalent circuits. And somebody said this ugly looking W, which is the diffusion component, named after Warburg, okay? Showing that that was very good for metallic electrodes. So this is when you have a metal electrode. Okay. But of course, that's what chemists do. And this whole study is called the Faradaic impedance in chemistry. Very big area, right? But Ted asked the question later on. He said, well, what happens if I want to look at a real rock? Okay, so I still want to get the eye here, but what happens if I put 2 electrodes and I put a rock in between? What's going to happen? Okay? And in one page of, I believe it's Madden and Marshall, in one page, he showed that if this rock was very thin, if it had it was a very small rock, you would get, I should write down here, this impedance here goes as 1 over F to the half. If it's a very thin porous rock, you get the impedance goes as 1 over F to a quarter. But Ted, in the generality in which he did mathematics, actually went further. And he showed if you took a big porous media, right, you would get that the impedance goes as 1 over F to the 1 over N. And that N tells you something about the porous media. It's usually about 8 or so for typical rocks. Now, it turns out that this problem, with just a thin coat on an electrode, was done in chemistry 10 years after Ted. And it's a classic paper in chemistry. I go to him with a paper. Ted, you need to read this, you see. You did something 10 years before this guy. Don't waste my time with that. Brad, you want to throw me off yet, or?
Yeah, it's about time.
I have one more item. Can I do inversion, or don't do it? Okay. Maybe I can just read it off. Okay. I have a couple of things here I have written down about inversion. One is, as best as I can tell, the inversion class that Ted started here is the oldest inversion class in the geosciences, certainly in the US. Okay? It was original in many ways. All of you will remember having to learn about Langsos. Okay? Well, today everybody uses something from Langsos, which is the SVD, the singular value decomposition. Ted actually introduced that. You tell that to an electrical engineer or anything, and they think, you guys are crazy that that came from. But he understood the importance of it, and it kind of leaked out from here everywhere. So a lot of important things happened there. Another thing that we all learned in that class is how to transform a problem into a logarithmic problem. And it changes very much the way in which we do nonlinear problems. It turns out it's never been published. As such, I mean, many of us use it. And it's an old secret here we have for 50 years or something like that. It's a transformational thing. Some things you can't do without the logarithmic transformation. Best as I could tell, it's a TED invention. Okay? Brad mentioned Kayaki and Ted Madden teaching this class together. It was quite extraordinary. Both men, very confident of themselves, great guys. And Kayaki spent 2 lectures completely talking about the WKBJ integral, mostly used in seismology and so, but any type of wave phenomena. So we all, took the notes and everything, and on the end of the second day, before we left, Ted said, hold it. And, he called Keitiaki, K, next session, I'm going to show you how to do this in 10 minutes. Okay, all right. So Kay said, okay. And we came back the next day. I don't know, Tom might have been in that same class. I can't remember. We came back next day. And so said, 10 minutes exactly, Ted showed how to do it. And Kay sat down speechless. And he said, okay, Ted, okay. So I'll end by saying a last inverse problem, although I wanted to say something about John Claerbout. When I did inverse problems, I was not fortunate like Brad. I got a B. Okay? I think partly because I'd never done a term paper in my life. I didn't know what this thing was about. I thought it was a lot of foolishness, term papers. Okay. But I spent my 5 years. I got my degree. We had a big party on the top of Eastgate here tonight. And in the middle of the party, who comes? Katie Aki and Ted Madden together. And they have a plastic bag, you know, nothing stylish at all. And what they had done was they had to go to the president of MIT, which was Charles Vest. He's the only person who can change a grade. And they changed it to an A for me. You see how hard I had to work to get my A. All right. The last thing I want to say, because it has a nice way in which it can go forward. John Claerbout once told me in an elevator at Stanford, he said, you know, Dale, I don't know if this ever happened to you with Ted, but sometimes he tells you something. You don't have a clue what this guy has said to you. Q, he said, but you know, we have good memory, we remember it. And he says, sometimes 10 years later I'm working. And I said, oh my God, Ted told me this 10 years ago. It's so true. And I want to leave you with that thought that because of that, Ted is going to be with us for a long time. We're going to still remember things that he said to us that we didn't understand at the time. Thank you.